roots of complex numbers. So far, given a complex number z, we've been able to find expressions of z to the power of n using de Moivre's theorem. Now, we'll be faced with a problem. Given a complex number to a power, how do we find the solutions for z? And in order to do this, we need de Moivre's theorem. So let's go ahead and write it down. So if we have some complex number and raise it to a power of n, it's just going to be the modulus to the power of n outside of cos of n theta plus I times sine of n theta. And we're going to use that to help us. So let's look at our first example. We want to find all the cube roots of 1. So the first thing we need to do is construct an equation. So if we're after the cube roots of 1, we're going to let z cubed equal 1. And this should work because if we cube root both sides, we'll have the cube root of z cubed equals the cube root of 1, where the cube and the cube root will cancel out, and we get our solutions of z being the cube root of 1. So this is the correct equation we need. Now, in order to solve this for z, we're going to need to so obviously the obvious solution is just to cube root both sides, and we actually do get z is equal to 1. So that is one solution, but because it's a cubic equation, we're expecting 2 more solutions. So these are the ones we're trying to find, and these will be complex solutions. So one thing we want to do first is we want to let z equal r outside of cos theta plus I sine theta, and we want it to be a root of the equation. And this just helps us get a complex number solution. This is just the mod-arg form of a complex number. But if we're going to let this be a root of this equation, that means if we sub in this value for z, the equation will hold true. So that's what we're going to do. We're going to have r times cos theta plus I sine theta, all to the power of 3, equals 1. Now we can go ahead and use de Moivre's theorem. So we get r cubed times cos 3 theta plus I sine 3 theta equals 1. Now, before we go any further, we're just going to look at some useful things to know. If we ever want to express just the number 1 in mod-arg form, we can write 1 as 1 outside of cos 0 plus I sine 0. And while we're here, if we ever want to write minus 1 in mod-arg form, that's just going to be cos pi plus I sine pi. And hopefully this makes sense, because on an arcGAN diagram, if you want to be at the point 1 on the real axis, you'd have to have an angle of 0. And if you want to be at the point minus 1, you need an angle of pi. Now, let's go ahead and change our 1 using this. So we're going to get r cubed outside of cos 3 theta plus I sine 3 theta equals 1, which we now know we can write as 1 outside of cos 0 plus I sine 0. And now we want to equate things on both sides of our equation. So we can say that r cubed must equal 1. We want to now equate our real part inside the bracket with our real part inside this bracket. So we can say that cos 3 theta must equal cos 0. And we can say that sine 3 theta has to equal sine 0. So if we cube root both sides over here, we just get r is equal to 1. Let's tidy up our cos theta. Our cos 0 is just 1. And sine 3 theta is just going to be 0. Now solving for 3 theta here, we're going to have 3 theta equals the inverse cos of 1. We need to think about all the values where our values of our angle of the inverse cos of 1. So cos equals 1 when our angle is at 0, 2 pi, 4 pi, and so forth. And for sine, we're going to have 3 theta equals the inverse sine of 0. So 3 theta, so we've got to think about where sine is equal to 0. So sine is 0 at 0, at pi, at 2 pi, 3 pi, and so forth. But we need values that match up. So 0 matches up, pi does not match up, and 3 pi does not match up, so it's only every 2 pi that the values match up. So we can therefore conclude that 3 theta has to equal 0 plus some multiple of 2 pi. So we can write it as 2k pi. And then we can go ahead and divide both sides by 3. So we get theta equals 2k pi over 3. And now we've got everything we need to find our answers to our equation of z cubed equaling 1, because we let z equal r outside of cos theta plus I sine theta, and we know the value for r and theta now. So let's go ahead and sub those in. So we get z equals r, which we know is 1. So then we get cos of theta, which we know is 2k pi over 3. So and these values for k were 0, plus or minus 1, plus or minus 2, and so forth. Plus, over here, we get I sine of theta, which is 2k pi over 3. Now, we're not done yet, because here we have a cubic equation. And we only want 3 roots. There's only 3 roots we're interested in. So we just want to go ahead and select 3 values of k that we can sub in and only get 3 answers. So we always start with k equals 0. And then we go in increasing order. So then we can use k equals minus 1 and k equals 1. And after this, the other values of k still work, but they just end up repeating our solutions. So subbing in all these values of k, we're going to get, so if you sub in 0 for k, we're actually going to get z equals 1, which we got that straight away as a solution. Subbing in minus 1, we're going to get z equals cos of minus 2 pi on 3 plus I times sine of minus 2 pi on 3. And subbing in k as 1, we're going to get z equals cos of 2 pi on 3 plus I times sine of 2 pi over 3. And these are our 3 solutions to our equation, z cubed equals 1. and one of them being a purely real number. We're going to go ahead and plot these on an Argand diagram. And what you'll find, plot them with the real and imaginary axis, you'll find that they all lie on a circle centered at the origin with a radius equal to r. In this case, the radius is 1. So this radius is 1. And if we plot these out, we can use our angles to determine it. So when k was equal to 0, our angle was equal to 0. So our first root lies there, and that makes sense because that's where z equals 1. Our next one, when we had minus 2 pi on 3, that's about here. And 2 pi on 3 is there. So 2 pi on 3 in degrees is 120. So if we draw these out, we get 2 pi on 3 minus 2 pi on 3. And this angle in between here is actually also equal to 2 pi on 3. So it turns out that the roots are perfectly evenly spaced with each other on an Argand diagram, and they're a distance from the origin equal to r. All right, let's have a look at another example. We want the fourth roots of 1 plus 3i. So the first step is to construct an equation. So we're going to say z to the power of 4 equals 1 plus 3i, which would make sense because if we fourth root both sides, we'll end up with z equals the fourth root of 1 plus 3i. And it's exactly what we're after all solutions of z where this is true. Our first step, or our next step, is to let z equal r outside of cos theta plus I sine theta. So we want it in mod arg form, and this is going to be a root of the equation, which means that if it's a root, we can sub it into our equation and it'll hold true. So we get r outside of cos theta plus I sine theta, all to the power of 4 equals 1 plus 3i. Let's go ahead and use de Moivre's theorem. So we're going to get r to the 4 outside of cos 4 theta plus I sine 4 theta equaling 1 plus 3i. Now, it'd be more useful if 1 plus 3i was in mod arg form as well, so we could equate the sides with each other. So we can go ahead and do that. So we can we'll do it up here. We'll go over here. We'll say 1 plus 3i. It's going to be, so let's find the modulus of this by doing the square root of 1 squared plus 3 squared. So we're just going to get, sorry, the question was actually 1 plus root 3i. So let's just go ahead and just fix that up. No harm done just yet. There should be a root in there. Okay. So we're going to have root 3 all squared, just so we get a nice number out of this. So this is just going to give us root 1 plus 3, which is 4. So we're going to get 2 for our modulus. And we can get our argument by doing the inverse tan of our imaginary part over our real part. So this is going to give us our argument, and this is going to give us pi on 3. So now we've got r to the 4 outside of cos 4 theta plus I sine 4 theta. So we can rewrite this in mod arg form now. So we can rewrite this as 2 outside of cos of pi on 3 plus I sine pi on 3. And we can go ahead now and equate some things. So now we can equate our modulus on both sides. So this must mean that r to the 4 equals 2. So r is the 4th root of 2. And we have cos 4 theta must equal cos pi on 3. And we also have sine 4 theta equaling sine pi on 3. We can just equate angles now, because if cos 4 theta equals cos pi on 3, that means 4 theta has to equal pi on 3. And we get the same thing for sine. Dividing both sides by 4 gives us theta equals pi on 12. And remember from last example, this has to happen at every multiple of 2 pi. So we write it as plusing 2k pi, where k equals 0, plus or minus 1, plus or minus 2, and so forth. And since we found our angle and our modulus, we can sub that back into our original equation for z being a root. So we get z equaling the 4th root of 2 outside of cos of pi on 12 plus 2k pi plus I times sine of pi on 12 plus 2k pi. And now, because it's a power of 4 equation, we need 4 solutions. So we need to go ahead and sub in our values of k in ascending order. So we're going to start off with k equals 0, then go to k is minus 1, k is equal to 1, and k is equal to minus 2. And if you do that, you'll end up with z equaling the 4th root of 2 outside of cos of pi on 12 plus I sine pi on 12. We'll have z equals the 4th root of 2 outside of the cos of minus 5 pi on 12 plus I sine minus 5 pi on 12. Z equals the 4th root of 2 outside of the cos of 7 pi on 12 plus I times sine of 7 pi on 12. And finally, z equals the 4th root of 2 outside of cos of minus 11 pi on 12 plus I sine of minus 11 pi on 12. We're going to plot these on the Argand diagram just so we can see what's going on. Now, just going to do a rough plot with a real and imaginary axis. Now, all of these lie on a circle where the radius equals the 4th root of 2. Always, they're all evenly spaced. And at our angles of this one at pi on 12, this one at 7 pi on 12, this one here at minus 11 pi on 12, and this one here at minus 5 pi on 12. So we get all of these. Now, this diagram isn't to scale, but all of these are evenly spaced, so they're all separated by right angles because there's 4 of them. And there's no conjugate pairs because the equation involved non-real coefficients. So there's no conjugate pairs. Last time there was a conjugate pair because we only had real coefficients. So just before we finish here, just realized made a bit of a mistake. So let's just fix it up. So when we divided both sides by 4 over here, forgot to divide the 2k pi by 4. So dividing that by 4 actually gives us theta equals pi over 12 plus k pi over 2. And all we need to fix up here is that this should just be k pi over 2. So let's get rid of that and get rid of that. And these values they're all fine because I was looking at my piece of paper here, so I know they're all good. Okay. We're going to look at something called complex roots of unity. So complex roots of unity. And we've actually already looked at our first example, but here we're going to just generalize it a bit. So if we have some complex number w and it's to the power of n equaling 1. Actually, let's come back to this. Let's just investigate what happens if we have w squared minus 1. Well, we know we can factorize that into w minus 1 multiplied by w plus 1. It's just a difference of 2 squares. What about w cubed minus 1? Well, that's actually w minus 1 outside of w squared plus w plus 1. What about w to the 4 minus 1? Well, that's w minus 1 times w cubed plus w squared plus w plus 1. And we could keep going here. Hopefully you can recognize the pattern. But the general pattern is that if we have w to the n minus 1, we can write that as w minus 1 outside of w to the n minus 1 plus w to the n minus 2 plus ... all the way down to w squared plus w plus 1, depending on what your n is. And this really helps us. This can help us when we have something called complex roots of unity. So where we're looking at complex numbers to some power equaling 1. Because what we can do is we can subtract the 1 from both sides. So we get w to the n minus 1 equals 0. And we know we can rewrite w to the n minus 1 using these factorizations. And this can help us analyzing equations without even finding any roots. And that's what we're going to do now with one more example. So let's say we've got w is a non-real root, so it's a non-real root of unity. Our first question is we want to show that the conjugate of w is also a root. So that means if we have some equation, z cubed equals 1, because this is a cube root of unity equation, we know that w is a non-real root of unity, which means that we could sub in w and the equation would hold true. So this equation would hold true. And we want to show that the conjugate of w is also a root. So let's go ahead and take the conjugate of both sides, because it'll still be true. So we'll take the conjugate of w squared and the conjugate of 1. the conjugate of 1, well, we can think about 1 as just being 1 plus 0i, and the conjugate of this is 1 minus 0i, which is still equal to 1. So we know the conjugate of 1 is just also 1. And we have our some conjugate theorems that one of them states that if we have a conjugate times a conjugate times a conjugate, it's the same thing as multiplying all our terms and then taking the conjugate of all of those. So that means that the conjugate of w cubed is also equal to the conjugate all cubed. And if that's the case, that also means that the conjugate of w satisfies the original equation. So therefore, the conjugate of w is also a root. Now, our next part is to show that 1 plus w plus the conjugate of w equals 0. Now, to do this, we know that w is a root and the conjugate of w is a root, and actually 1 is also a root because we know 1 cubed is also equal to 1. So these are just the sum of the roots. Just to help us visualize things a bit better, let's rewrite our z cubed equals 1 equation in terms of a polynomial looking equation. So we could rewrite this as z cubed plus 0z squared plus 0z minus 1 equals 0. So this is just the sum of the roots, because they're all three of the roots. So we know the sum of the roots, 1 plus w plus the conjugate of w equals minus b over a, so we're going to get minus 0 over 1, which is 0. What about, we want to show that 1 plus w squared equals 0. Now, to do this, we know that w holds true in our equation, so we get w cubed is equal to 1. Let's go ahead and minus 1 from both sides. So we get w cubed minus 1 equals 0. Then we can use our factorization, our important factorizations that we just learned, to rewrite this as w minus 1 all times w squared plus w plus 1 equals 0, which means that either w minus 1 has to equal 0 or w squared plus w plus 1 has to equal 0. We have to go back all the way to our original question to see that w is a non-real root. And if we were to solve this equation, it would imply that w is equal to 1, but it can't be a real number, it has to be non-real, which means that this equation here has to be true, and we've shown that 1 plus w squared equals 0. Finally, let's show that 1 plus w squared, all cubed, multiplied by 2 plus 3w plus 3w squared, all equals 1. So we're going to use the parts that we've previously got. So we know w cubed equals 1. And we know 1 plus w squared equals 0. And from this equation, we can probably rearrange it to help us out a bit better. So we know that 1 plus w squared equals minus w, just by minusing w from both sides. And we know that w squared plus w will equal negative 1 by minusing 1 from both sides. So these might come in handy. So let's just take our left-hand side. So we know 1 plus w squared equals minus w. Now we're going to rewrite 2 plus 3w plus 3w squared to help us out a bit. Or actually, let's factorize out the 3 out of just the last two terms. So we have w plus w squared. Then, so this should be cubed. Now, minus w all cubed just equals minus w cubed. Then we're going to have 2 plus 3. Now we know w plus w squared equals minus 1. Now we know w cubed equals 1. So we're just left with this to evaluate. So we get minus 1 outside of 2. 3 times minus 1 is minus 3. Minus 1 times 2 minus 3 is minus 1. And minus 1 times minus 1 is 1, which equals the right-hand side.